name is Saraswati Rajendran and my team members are Sumita and Shivi Shankari. So today we'll be presenting the question 14 in the organic spectroscopy group assignment. So as you can see in this question, there are 4 spectrums given. So the first spectrum is the MS analysis, where we can know about the molecular weight of the unknown compound. The second spectrum is FTIR analysis, where we can know about the functional group of the compound. And the third spectrum is the carbon-13 NMR analysis, and the last spectrum is the proton NMR analysis. So through this spectrum 3 and 4, we can know about the structural formula of the unknown compound. So let's move on to the first spectrum, which is the MS analysis. So as I said earlier, we can know about the molecular weight of the unknown compound, because when a high energy electron bombarded on the molecule, the compound tend to lose an electron. So this compound will form a radical cation, which is also known as a molecule ion or the parent ion. So let's look at the spectrum. So we can see a base peak at 100% intensity is present at the MZ of 31, and a molecular peak is present at the MZ of 60. So from this we can know that the molecular weight of the unknown compound is 60 gram per mole. And there are also other fragment ions present at the MZ of 27, 29, 41, 42, 39 and 59 MZ. So let's move on to the next spectrum, which is the FTIR analysis. So as I say, FTIR analysis will help us to identify the functional group present in the unknown compound. So as you can see, at the frequency of 3350 cm-1, there is a presence of OH group. So this shows that this compound has high possibility of being an alcohol compound. Next wave number is at 1860 cm-1, that you can know the presence of CsP3H stretch. So this shows that the compound is an alkene compound, and at the wave number of 970 cm-1 and 1068 cm-1. So in this wave number, we can see the presence of strong CO stretch. So this shows that the carbon is strongly bonded to oxygen, and therefore it has high possibility of being a primary alcohol compound. So in summary, we can know that the compound has the OH stretch and also CO stretch. So we can say that the compound has high possibility of becoming a primary alcohol compound. And the further analysis on the structural formula of the compound can be analyzed in the next 2 spectrum.
Thank you, Sarvesh, for explaining about FTIR and mass spectroscopy for me. And my name is Sumita Murugan. I will be explaining on 13C carbon NMR spectrum. So let's get into it. So we will start with the chemical shift of 10 ppm. The value of the characteristics we can say as sp3 hybridized carbons. Specifically, we can say it as methyl groups. So we can say methyl groups are located in upper field for 13C NMR because they are highly shielded by the electron density. So we can remember that the 0 point is definitely by the methyl carbon in TMS, which is served as the reference standard. So let's continue. Next, we have a chemical shift of 30 ppm. This is also within the sp3 carbon hybridization, but in this case, it is inductively we can say it as methylene group, which because just now it was methyl group, now it's methylene group CH2. This shift at 30 ppm suggests this carbon is bonded to a different alkyl group or hydrogen without directly bonding to a highly electronegative atom or a pi system. Now let's consider a chemical shift of 70 ppm. So automatically it's considered as downfield compared to the previous example, and is characteristics of a carbon bonded to an electronegative atom such as oxygen in an alcohol, C bonded with OH. It's like that. So the oxygen atom de-shields the carbon, pulling electron density away and causing a downfield shift. Alcohols, whether primary, secondary or tertiary, all appear in this region. So for a better understanding about this shift, let's review the key components of this 13C NMR. So we have like majorly 3 points where we can say that shielding and de-shielding plays a major role in this, because electron donating group shield carbons and shifting signals upfield. So electronegativity group, which is a de-shielding group, shifting a signal downfield, which means lower ppm means they have upfield, downfield means they have higher ppm. So as for the second point, which is we can say that's hybridization. sp3 carbon are upfield, while sp2 and sp carbons are appeared as downfield. And for the third point, functional group. Each functional group has characteristics of chemical shift. For an example, carbonyl group as C double bond O appears between 160 to 220 ppm. So let's summarize this. We analyze the specific shift of 10 ppm, 30 ppm and 70 ppm, which means 10 ppm which shows there's the presence of CH3 group, and for the 30 ppm there's a presence of CH2 group, and for the 70 ppm there's the presence of C bonded to OH group. So along with it, we are covering about the shielding and de-shielding effect, hybridization and functional groups, and other key points that makes 13C NMR is in a valuable tool to found a structural analysis. So that's it for this spectrum, and my groupmate Shivi will continue with the next spectrum for H proton NMR.
Good day everyone, I'm Shivi. Today we are going to explore proton nuclear magnetic resonance, or HNMR, a technique widely used to analyze the structure of organic compounds. So in just 5 minutes, we'll dive into how NMR works and how they interpret signals and uncover what they reveal about the molecular structure. So firstly, NMR relies on the unique properties of hydrogen nuclei. These nuclei have spin which allows them to interact with the magnetic field. When placed in an external magnetic field, they align either or against the field. By applying radio frequency radiation, we can flip these spins, generating signals that we measure in an NMR spectrum. Moving on, NMR spectrum provides 4 critical pieces of information, which are number 1, number of signals. This tells us how many distinct types of hydrogen environment exist in the molecule. Secondly, it's the portion of signals, which are also known as the chemical shift. The chemical shift indicates the chemical environment of each type of hydrogen. Third, the relative areas, or also known as the integration. This tells us the number of protons in each environment. And lastly, splitting patterns. This reveals the number of neighboring hydrogens following the n+1 rule. For example, a triplet suggests 2 neighbors. Looking at the spectrum based on the analysis, the signal at 0.8 ppm has low chemical shift, suggests a shielded environment, typical for an alkyl CH3 group. Its a triplet splitting pattern indicate coupling with 2 neighboring protons from a CH2 group. Integration of 3 confirms the presence of 3 equivalence protons. Moreover, the signal at 1.6 ppm is slightly higher chemical shift, points to a CH2 group adjacent to a CH3 group. The quarter splitting shows it's coupled with 3 neighboring CH3 protons. Integration of 2 confirms 2 equivalent protons. Moving on, the signal at 2.3 ppm shows a singlet which no splitting indicates no neighboring protons. The integration of 1 suggests that this could be also an OH group. In addition, the signal at 3.6 ppm, the higher chemical shift indicates a CH2 group near an electronegative atom. The triplet pattern reveals coupling with 2 neighboring CH2 protons, and the integration of 2 fits this environment. To summarize, proton NMR spectra are rich with structural information where the chemical shifts tell us about the electronic environment. The splitting patterns reveal neighboring hydrogen. Moreover, the integration indicates the number of protons. These aspects work together to unravel molecular structures. In a nutshell, proton NMR is an indispensable tool in chemistry which bridging the gap between molecular theory and practical identification. By analyzing signals, we gain insights into molecular informations and also functionalities. Thank you so much for the attention.
Hi everyone, it's me back again. So let's conclude now. So as you can see, this is the structure of the unknown compound. So in conclusion, we can know the molecular weight of the compound is 60. So when we calculate the carbon, hydrogen and oxygen present in this compound, we can get the molecular weight of 60 gram per mole. And second is the FTIR analysis. We can know that the compound has a presence of CO stretch, CsP3H stretch and also OH stretch present. So therefore we can also confirm that this structure is really a primary alcohol compound. And from the carbon 13 NMR also we can know that the carbon has a chemical shift at 30, 10 and 70 ppm. So from the structure also we already know that the 10 ppm, 30 ppm and 70 ppm carbon is present. And finally the proton analysis. From the proton analysis we know that there are presence of 10 hydrogens, 3 carbons and 1 oxygen. So as you can see the structure is also confirmed. Therefore we can conclude that this structure is a propanol with a chemical formula of C3H7OH. And that's all from me. Thank you.